everyone, this is Dr. Sirisha working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to discuss about few terminologies which are relevant in data structures related to linked list. Let's see what a linked list is. Before going to the basic definition and how to work with a linked list, let us understand what were the limitations of an array which led a path to reach linked list. The basic disadvantage with our arrays is even though the data is linear in structure, that is, data is stored in contiguous memory locations, with the help of indexing, we can reach any indexed value at any point of time with just one click, one line of code we can reach. But the basic limitation is its fixed size. That is, before initializing any or start working with any array with its definition, we need to give a size for it, which is fixed. If you want to extend dynamically, you can extend it, but you need to give or initialize a size of it when you start working with arrays. That is one of the limitations with arrays, which is not with lists. I'm not saying linked list, it's lists. So one point you need to think. In C programming, we talk about arrays which are homogeneous in nature. Coming to Python, we talk about lists which are heterogeneous in nature, right? So when we work with arrays or with the list, the size will be fixed initially, which can be extended in the future, right? Second is the data is to be physically stored in contiguous memory locations. That is one of the drawbacks. Why it is a drawback is if you are trying to store huge amount of data, then finding contiguous memory locations is quite difficult. Coming to the third and the most important limitation of arrays is insertion and deletion operation. Even the search operation is very easy, but insertion and deletion will be quite difficult. Let me explain you the same with the help of a small example. Okay, so let us consider an array. Okay, let this be an array with few elements. Say A, B, C, D, E, F, G, and H. And their index values are 0, 1, 2, 3, 4, 5, 6, 7. Now, my task is to insert. What element you want to insert? The key is, say, X, and let the position be some second. Okay. Second position, I want to insert X. Then what the resultant list you are expecting is, as X is supposed to be in the second position, that is at the index value 1. So A, X, B, C, D, E, F, G, H is the list which you are expecting. So even though you have abundant empty space which is not used in the array, then have to insert. Only point is swap the elements. Swap the elements money. The element at 7th index will be written on 8th index. The element at 6th index will be overwriting the element at 7th index, G. Then the element at 5th index will be shifted towards right. Element in the 4th will be shifted right. So this is how you are going to provide space, right? So B and C. Now you can see that actually here B will be there, which you are going to overwrite with your element which you want to insert, which is X. See how many shift operations you have done to insert an element at a given position. Appending is easy because append means inserting the element at the last by default. Whatever the length of the array may be, by default inserting an element at the end is appending. So you need not think of swapping elements. It is not required. But inserting at a given position is a tedious task in case of arrays, right? So this is one of the drawbacks. And say if this is your list, and rather than inserting, you want to delete an element. That is, you want to delete an element at a position 2, which is X, which you have recently inserted. So if you remove it, is this the final one which you are expecting with an empty space at index 1? No. You have to shift the elements towards left. B is going to overwrite X, C will be overwriting B, D will overwrite C, E will overwrite D, and so on. Right? If the list with which you are working, say the size is 100 and you are trying to delete an element at position say 5. So how many left side swaps you have to do? It is a very time consuming process. So the many shifts of data is required. One glitch will bring disasters into this one, right? So these are the basic limitations of arrays, right? So which we are going to overcome when we work with linked list. Even though linked list suffers few limitations, but when compared to few applications where you have huge data to store, and we already know that we are going to insert new data and we are going to delete few data. That is, you are going to modify the existing data, right? So in that case, linked list comes into the picture. The basic advantage or the limitations which the linked list overcomes is dynamic size. Very simple, that straightforward point is dynamic size. You want to insert an element or delete an element, you can clearly for insertion create a node, insert the data and build the relations, right? Delete a node, reframe the relations, free the amount of memory allocated for that node. It's very simple when compared to linked list. You need not touch the existing data, either if you want to insert a node or if you want to delete a node, right? So that is one of the advantages. And the next advantage is, as I said, dynamism is important, and ease of insertion and deletion, right? Search operation also is quite easy. Start from the first node and keep on hopping unless you reach a node whose data matches with your key, right? So all the operations, one compared to arrays, it is quite easy to implement with linked list. So with a note on the limitations of the linked list, limitations of arrays, how a linked list overcomes it, let's start linked list. So linked list is also a linear data structure, but the data is not stored in contiguous memory locations, right? So there are three types of linked list which we can see. One is single linked list, double linked list, and circular linked list, right? So let me explain you these three categories with a small picture. Have a look at this one. The first one, single linked list. You can see that we can run only in one direction, that is forward direction, right? So here, from starting from the first node, with the address of the next node in its hands, we can take a hop and move only in the forward direction. Any node whose address part or link part is null or none, we can say that it is the last node, or it is not having any node next to it. Thereby, it becomes the last node of its kind, right? So this is simply a single linked list, which is unidirectional. So the basic drawback with single linked list is, say you are at the last node and you want to reach the first node, or say the second node. So your current position is at the last node and you want to reach the second node. Rather than going to the start and fetching the address of the first node and taking the hops, you can directly move from the last node to the first node. That is, the last node, if it holds the address of the first node, then it is quite easy to move from the last node to the first node. That is the advantage of circular linked list, right? Rather than starting the job from the scratch, even you can run from last node to the first node also. But still, circular linked list suffers with the drawback which we have seen in single linked list, which is a unidirectional nature. Okay, unidirectional nature, which double linked list are going to overcome. Have a look at a node in a double linked list. It has 3 parts. Data part, it is the usual part which we generally have, and its left side will be left address part, which holds the address of the node which is left to it, and right address part which holds the address of a node which is right to it. Means with the help of these address paths, you can move forward as well as backward. In both the directions you can travel, right? So these are the 3 types of linked list we find, right? So let's start working with the single linked list. Before going to single linked list, let me explain you what a node is. I was keep on telling you single linked list nodes, how they are linked, blah blah blah. But what a node is, let me explain you the same. Node is nothing but collection of data, you can think. Collection of data, collection of simply, in case of single linked list, collection of 2 items. One is the data part, the data which you want to store. Second is link or the pointer. A pointer which holds the address of the next node, right? So a combination of data and link part is nothing but a node, right? And the second terminology which you need to think of is the head. Or in few textbooks you also read it as stat. Then what is this head and stat? As we all know that linked list do not have index values because the elements are scattered throughout the memory, and no data piece node, or you say database or node, whatever, cannot reach the other node unless it have the address of its next node, right? So we cannot assign index values to them. Linked list suffers with that. Okay, so dynamically, randomly, we cannot reach any node. So we have to start with the first node. Even if you perform insertion operation, deletion, search, reverse, rotate, whatever operation you want to do, you can do. But the condition is you have to start with the first node only. Where we have the address of this first node. As linked list always talk about addresses, right? So head or start is the pointer variable which holds the address of the first node, right? Which holds the address of the first node. From there, we are going to start our journey, right? So in the books, different books, you'll find this terminology, because if you say head, why? Because it is going to head the list, whatever the linked list may be, circular, single or double. As it holds the address of the first node, it is the head. If you say that from it is the pointer variable from where we start our work, right? Any operation you want to do. So if you call it as start. I feel start is a relevant word, but it is not mandate, guys. You can call it as head also, right? And if you go through many books, authors change, the terms change, but the concept is the same, right? Let's move to what are the operations that we can perform on a single linked list. Whether it is a single linked list, circular or double, the basic operations that we perform will be the same. The first is to create. Okay. Then is to traverse. That is hopping from one node to the other to get the list of elements that we have. Okay. With the help of simple user-friendly statement like printing the data, we can cross-check whether all the nodes are there, all the data pieces are there or not. Okay, then inserting an item or deleting an item, or concatenating, and if you go on, you have many like reversing, sorting, or searching. Many operations are there, but the basic ones are these two: insertion and deletion. After creation, creation will be the primary to check whether you have created it properly, or inserted an item properly or not, deleted an item properly or not. You need the traversal, right? So these are the four basic operations that we have, right? Let's go through them one by one. So then have to create a node, right? So that is the main point. With the help of Python, which is having the advantage of being object oriented in nature, let us create a node first of all, right? So I have taken the class node, and in its constructor, I have taken an argument data, right? So whenever I'm going to create an object of class node, I'm going to pass a key value to it so that that behaves as a data and gets assigned to one of the member variables of class node, which is data. And we all know that node have two parts. One is data part, the other is next part. Next is nothing but the link part, which holds the address of the next node, right? But we know that initially, when we create a node, this node is a newborn one, and it is not linked to any other node. So its next part will be initialized with none. So have to call this one. It's a very simple statement. If the object name is a new node followed by the name of the class followed by the key value that you are going to pass to it. This is nothing but creating an instance of the class node, which is nothing but an object, new node, right? This call is going to raise or invoke the constructor, thereby data and next will be formed like this. Data will be filled with the key value that you are going to pass, and by default, the next part will be filled with none. Okay, this is how we are going to create a node. Coming to the second class, the first class node is meant only to create a node. In the second class, I'm like single linked list or linked list, whatever the name you want to give a relevant name. With that, I'm going to start a constructor of it where start is filled with none. Why? We know that start is a pointer variable which holds the address of the first node, right? It holds the address of the first node. Initially, no node is yet been created, only start pointer is created. So as node is not created, how can it point to some random address? It cannot point to some random address, right? So it is initialized to none, saying that the list is empty right now. So once you create a node, then you can build the relations, right? So let's check it out. Right. So I have to create a list. It's an important point. Have to create a list. Say 3 nodes I want to create. So I'm going to run my loop for all the three times I'm going to run, right? So I have read the data value which I want to insert, and I have created an object or an instance of the class node. So thereby a node is created with the data and none as its parts, right? Now, here we encounter 2 cases. A case where list is not yet prepared, is not yet created, right? And the case where you have handful of elements, and where you have handful of elements. So the first case is a case where there is no list yet been created, right? So start is none is the condition which will help you that. Means if the start pointer is filled with none, that itself says that there is no list yet been created. If there were elements in the list, then start would be holding an address. That is particularly the address of the first node. If it is none, then obviously there is no list. It is an empty list, right? So as soon as you feel that the start is filled with a none, store the address of the new node inside it, because it is the first node of its kind. Okay. The second case, a case where you have handful of elements. When you have handful of elements, name the first node as temporary and reach the last node. That is, here I'm very particular while creating the list. I'm going with append operation. That is inserting an element at the end by default. Okay, fine. I'm using while loop. I'm going to take the hops such way that unless I reach the last node, I'll be keep on taking these hops. Then how to identify the last node? Very simple. The last node, its next part will be none, because it is not pointing to any other element. So its next part will be filled with none. That is, the link part will be filled with none. Once I reach a node, that is the last node particularly, I'll store the address of the new node in its next part, building a new relation or appending a node into the linked list, right? So this is how I'm going to create a linked list. Coming to a small animation on how to create. So initially, if the start is none, it is case 1 I'm talking about. So when we create a node, store the address of the node in the start. Thereby, you have created a relationship between the first node and stored its address in the start. You have built a relation between the start pointer and the new node, right? Let's look at the case 2, that is inserting a node at a tail, right? So this is the list which I'm having in my hands. That is 21 is related to 22, right? So you can clearly see that node 22, right? Its next part is filled with none. Why none? Because it is the last node. There is no other node after it, right? Very good. So what happens is, take the hops as I said, make the temporary sit on the node whose next part is none. Now store the address of the new node inside it, which is 4000. Now with this, by just storing the address of new node in temporaries next, we can say that we have built the relation between the new node and the temporary node, right? As the new node is already having its next part filled with none, it is obvious that it is the last node now, right? Yes. This is how I'm going to create a linked list. Right. After creating, we have to, as I said, insertion and deletion are the two primary operations in case of linked list. So there are many ways to insert. The three are basic are inserting a node at the front end. That is, if you have a list like 20, 21 and 22, and you want to insert an element at the front end, say 19, insert 19 at the front end. The list should be 19, 20, 21 and 20. This should be the resultant one. Okay, what if you want to insert this 19 at the end? Then this should be the resultant one. 20, 21, 22 and 19. What if you want to insert 19 neither at the end nor at the front but at position 2? Then it must come at position 2. Then the resultant should be like this. Have a look. 19 is sitting at the second position. So these are the three different cases in case of insertion. Guys, if you want to go in depth, you will find many cases here also. So read a position, okay, and say that before that position or after this position. As I said, many cases you are going to get, but the primary ones are inserting a node at the front, inserting a node at a given position, and inserting a node at the end. These are the three subcases of insertion. The same with deletion also. You can delete the element at the front end, the rear end, that is the last node, or a node at a given position. These will be the three deletion subcases in deletion, right? Let's look at them. So inserting a node at the beginning. So when you try to insert a node at the beginning, this will be the basic function for that. Read a value, create a node as usual. The first and foremost case is check whether the list is empty or not. If it is empty, that is, if the start is filled with none, make the new node with the start. Else, the second case, when you have handful of elements, make the first node as temporary, then store the new node temporary's address in new node next, and make the new node as the first node. Don't worry, I'll show you an animation on the same. This is the case where I'm going to insert the node whose data is 20 in the first position. First of all, I have stored the address of the temporary, that is the first node's address, which is 2000 in new node's next. Then I have stored the new node's address, which is 5000 in the start, because start is the pointer which holds the address of the first node. And I'm trying to change the first node by inserting a new node, right? Now the new node's address must be placed in the start. Good. So this is how I'm going to insert an element at the front end. Next, inserting a node at the end. So this is the one which you have just seen when creating a single linked list, right? Let's have a look at a small animation on the same. So let 20 be the node which is supposed to be inserted at the last. Okay, name the first node as temporary. Take the hops unless you reach the last node. Once you reach the last node, build the relation between the new node and the last node, right? So this is how we insert a node at the tail. Then the a bit difficult one is inserting a node at a given position, right? So here I have to read position also. Till now, the cases were like default ones where I was inserting at the front or rear. So there was no need to read the position, but I have to read the position here. And I need to use a function count, which will help me to get the number of nodes in my single linked list at any point of time. So with that, I'm going to start. Initially, I'm going to check whether the list is empty or not. If it is empty, then the new node will be the first node. Else, I have to check whether the position which I have read is between 2 and C minus 1, including them. Because if position is equal to 1, it means that I'm trying to insert an element as the first element which is already covered. And if the position is C, then I'm trying to insert element at the last, that is at the tail. Even this is covered. So I want a position which is between 2 and C minus 1, including them, right? Only in that case, I can insert. So to insert at a given position, say if the person gives a valid one, I need to hold two positions now. A name to hold the node with at a given position, as well as a name to hold the node which is previous to that, right? So previous and temporary are the two different variables I'm going to use. So let's look at a small animation on the same. So here the list is something like this, 21 and 22, and at position 2 I want to insert 21. So this is the resultant which I want. I want to insert 20 at position 2. Let's do that. Right. So previous and temporary. I'll first give a say. Let me explain you in this way. So first node will get the names previous and temporary. Check whether the temporary position is less than the position or not. While I is the temporary variable which is going to hold one starting with the first node, and until unless you reach the node place where you want to insert the new node, you may keep on moving the temporary and previous such that previous is the name given to the node just behind temporary. Why I'm using this is I know that single linked lists are unidirectional. I can move in only one direction. So if I take a step ahead, I cannot touch the node which is behind me. To store the same, I'm using previous variable. Okay, next. So once I do that, I have stored two steps I need. I have to store the address of the new node in previous next. I have to store the address of temporary in the new node next. These are the two steps. Thereby, I have inserted the new node at position 2. Right? This is inserting a node at a given position. Next one, have to delete a node at the beginning. Okay, so to delete, first of all, the precautionary step is check at least the list is existing or not. That is case 1. If the start is filled with none, then I can simply say that list is empty and return. If it is not the case, and if you have handful of elements, then I would love to delete it, right? So how to do that? So take temporary is the name of the first node, and make the next address of the temporary be the new start. That is the name given to the second node of your list. That is the new starting node. Okay, let's have a look at the animation on the same. So here the list is 21 and 22. Now I want to remove the element 21. So I'm making the first element as temporary and temporary next as new start. That is the second one, right? So once I do that, I'll fill the start pointer, which is supposed to hold the address of the first node, with the address of new start 3000. Now start will be pointing to the new start, right? If I overwrite it 2000 with 3000. Very simple. Thereby, I'm going to use very simple statement like a delete of them. Thereby, I'm going to free the memory allocated for the first node. So this is how I can delete a node at the front end. So how to delete a node at the last. Even here, I'd like to take the precautionary step to check whether it is empty or not. If it is not empty, I'll go to the second case. So to delete the last node, I have to hop till the last node, right? So I'm going to use the while loop. I'm using while loop because I don't know how many number of nodes are there right now. So I'm using while. Okay, so here two nodes are there. So temporary and previous. Previous is the name given to the node which is just behind temporary. Okay, very good. Now, very simple. What do you expect, guys? So, previous, next, if it is filled with none, if this part is filled with none, the relation between temporary and previous is going to break. That's it. And you have removed the last one, right? So, this is how I'm going to remove. Simply, right? This is how we delete an element at the end. The next case is deleting a node at a given position, right? So here even again I'm going to use my count function and I'm going to check. The position which I'm going to read is neither 1 nor C. That is neither the case of deleting an element at the front end or at the back end. Once I get satisfied with that, I'll start my process. So say there are 3 elements in my list and I just want to remove the element at position 2, which is 22. If this is the case, then I'll travel or make my temporary be given the name to the element which I want to delete. Then previous next, that is this part, the previous next 3000 will be overwritten by temporary next. Very simple statement. Previous next is filled with the temporary next. What is there in temporary next? 4000. Place it in previous. So when you start, when you reach the previous node, it will say that its next node is at 4000 and you will be navigated to this element, overlooking the temporary node or the node which we actually wanted to delete. Now simply free the memory allocated for temporary and you delete that. Right? This is how we delete a node in it is given position in case of single linked list. Right? So then how to traverse? Or simply you can say display. After every insertion or deletion, any operation, you would like to see what is the current status of the linked list, how it looks like, right? For that, you need to traverse and have a look. Even here, I'll take a precautionary step to check whether a list exists or not. If it does not exist, fine, I'll just say that it is empty and I'll return. Else, I'll give the names temporary to the first node and take the hops until unless I reach the last node. And whenever I take a hop, I'll print the data part of it. Thereby, I can say that I have successfully completed the traverse operation. Right? So, what are the drawbacks? We have seen the functioning of a linked list. What are the operations that we are going to perform on that, right? So let's look at the basic drawbacks of linked list. The basic drawback is you might have seen that in case of every node will have two parts, which is data and link. Data part is the point which we need. What about this link? Link always stores the address of the next node. So the amount of memory required by the node to store the address is high. If you have say if the link node, that is the address, needs 4 bytes, if it needs 4 bytes, and if you have 4 such nodes, then 16 bytes will be used. What if there are 400? 1600 bytes will be used for the same. So as the node size increases, the amount of memory which is required to store the address of the next node also increases. Even if you want to store none for the last one, even that needs some memory, right? The same 4 bytes will be allocated. We never know when I'm going to append, right? So even that node will need 4 bytes. So huge wastage of memory is there in case of linked list. Next is random access. This is the one which I have said earlier, because linked lists do not have the indexing property. We do not have indexing. So if it was the case of arrays, if I say that I want an element at some ith position, then simply by retrieving the element in i-1 index, I can say that this is the value at your required position. Right? So it was quite easy, guys. It was quite easy. But now as the linked list suffers the same, we cannot do that. We cannot have the privilege of random access. Whatever element you want to reach, you have to start with the first node, and you have to keep on hopping until unless you reach the position or the data which you are searching for. So going with binary search, right? Binary search operation, that is by default a search in linked list is linear in nature, which is order of n. But binary search have order of log n complexity is, which is very less, but we cannot implement it using linked list. We can implement a binary search using only arrays. Why we cannot implement using linked list at every point of time? I hope you remember how we perform binary search. So there will be a huge list. So in this list, left and right positions and mid position you are going to take, compare the element pointed by the mid, and the prerequisite for this one is it must be sorted in nature. So many things are there, right? Which is not quite possible to implement with linked list. All times I'm going to break this list into two halves, right? So that is difficult when compared to the complexity raises. It will be no longer log n if you want to implement this logic, the binary search logic using linked list. It will be much more higher. Okay, then as the nodes are not stored in contiguous memory locations, so you cannot access the elements immediately. That is similar to the point which we have just discussed, which is a lackage of index values, right? So the time to reach a node increases, the time to reach. So we cannot implement CPU cache memory using linked list. Cache, what do you mean by cache memory? It is a small memory size which is used to, which stores the most frequently used content in that, so that rather than searching an element in the main memory, in the huge memory, searching for it, just go to the cache and search. If that element is there, as the cache memory is very small in nature, you can immediately retrieve, right? But if you implement cache memory using linked list, the time to search even in that small space also is very high. Forget about in the main memory. If you want to implement it using linked list, it is very difficult. It raises the complexity, that is the time complexity, exponentially, and even in case of space complexity also, it is very costly, right? So we cannot store the data using simply single linked list. We need to store the address of its previous node also. So we have to go with a double linked list, which is much more costlier, because every node will hold two address paths and one data path, right? So cache memory, which should be very fast in nature, if you implement with it or construct it using linked list, then gone. So linked lists are not suitable for accessing the data if you want it to be fast in nature or real-time hack situations I'm talking about. So these are the few drawbacks when you work with linked list. Okay, so let's look at the applications of the linked list. The basic applications are expressions is, first of all, polynomials. You can implement polynomials using single linked list. So what do you mean by polynomial? Any expression with the variable x, which can be represented in this way: a x bar n plus b x bar n minus 1, so on to k, where k is a constant, right? So such an expression is a polynomial expression represented by p of x, right? So where a, b, c, so on, k are the coefficients. K is a constant, a to j as per this expression are the coefficients. Then have to store. So here in this case, when you are working with the polynomial single linked list, here the node will have three parts now: the coefficient part, exponent part, and address part. So for example, if I want to store a x bar n, then it will be something like this. The coefficient is a, exponent is n, and this is the address of the next node. So this will be the structure, right? So polynomials will be implemented using single linked list. Okay, so have a look at this expression: 4x cubed plus 6x squared plus 10x. So 4, 3, address of the next node. 6, 2, address of the next node. 10, 1, address of the next node. 6, 0, address of the next node. you will not have an address for the last one because it is a constant, right? So this is how you can represent it. So all the operations, whether addition, subtraction, whatever the manipulations you want to work with the polynomials, you can do. This is simple code in Python to implement the same. So previously, to create a node, we had a two member variables, but now its constructor have three: coefficient, exponent, and next. By default, when I create a node, it will have three parts, say coefficient, exponent, and a none, because it is not related to any other node yet. The next class will be polynomial class, whose constructor will automatically have the start node, which will hold the address of the first node, right? Then to create, I have to read two values, the coefficient and exponent. I'll create a node and I'll pass coefficient and exponent as its parameters, and I'll return it. Okay, this is how I'm going to create, right? So, and the total creation of the polynomial, have a look at this one. So this is a simple piece of code which I have taken. Insertion at the end. Insertion at the end is the logic. Even you can go with insertion at the beginning also to create a polynomial. Okay, so this is a small function to display or to look at how the polynomial looks like. The other application is sparse matrix. Then what do you mean by sparse matrix? Any matrix, if the content 50% or more than 50% of its content is filled with zeros, then we call that matrix as a sparse matrix in nature, right? So size by 2, if it is having number of zeros is greater than or equal to size by 2, that is, size is number of rows multiplied by number of columns, then we call such a matrix as sparse matrix. For example, take any voice signal, if it is having any disturbance, background disturbance, and when we filter it, the voice parts will disappear as the graph. So, for example, this is an analog signal of voice, and over it, this is a small signal of voice. It is very and if it gets overlapped with the noise, when we remove this noise, we'll be removing the data part also here, right? We'll be forced to remove. If the data is sparse in nature, that means the most of its data is filled with zeros, we suppress. How we filter? We bring it, the signal, the top signal, the peaks to zero, right? So under that peak, your acoustic signals will be there, which will also be suppressed to zero. That way, we are going to lose the data. So, whenever you extract data from it, you will get sparse data. So, that is one of the major applications of sparse. We can work with the single linked list to store any sparse data. So, why we use sparse matrix is storage and computing time. So storage, if it is having more number of zeros, say for example, you have 10 by 10 matrix, that means 100 cells are there, and the data which you are having, that is values which are other than zero, whether positive or negative. Other than zero, if you have only just 20 elements, then out of 100, if you remove 20, 80 cells will filled with zeros. So why to store those zeros? Is it not possible to store only these 20 values, which is having some information? That is one. Computing time. So computing time will be logically decreased when you store only the required data and stop storing the zeros, right? So these 2 points, storage and computing time, will get reduced if you store sparse data rather than its actual form using single linked list. Let's see. So sparse matrix representation using 2D arrays you can do. Row, column and value will be its parts. Okay. So, and we have 4 different ways to represent any sparse matrix. We can do it using arrays, linked list, list of lists, and dictionaries. When we try to implement it with arrays, we have three parts: row, column, and value, as I said. Have a look at this one. So the index values of this matrix will be like this: 0, 1, 2, 3. So the data is over here. So its row is 0, its column is 2, and its data is 3, right? So if you consider, say, some random value 2, okay, its row is 3, column is 1, and data is 2. So see how many spaces you have used over there and how many spaces you have used when you are working with 2D arrays, right? It's quite easy. Even that suffers with storage, so linked list can also be used. So the structure goes like this. So the similar point, the row, column, the value, followed by the address of the next node. So 3 is linked to 4. Okay, the 4 is linked to 5. 5 is linked to 7. 7 is linked to 2. 2 is linked to 6, and 6 is the last one. So have a look at this one. The structure of the node will have row, column, value, and address of the next node. The same you can do using list of lists also, right? So it will be triples in nature. It will have column index, the value, and the address field. Have a look at this one. So here you will be having a node, each and every node, in such a way that it will have the column index, the value, headed by the address of the next node. Whereas it will have a list in its hands, which will hold the column values, right? So, row values. Row is maintained in terms of a list, column, value, and address, and then another list. So, list of lists embedded one inside the other. Even like this also, you can store the data. And the next but last not but least one is using dictionaries. This is explicitly I'm talking about the case of Python, my dears. Using dictionaries in Python, you can store a sparse matrix. So how dictionaries? Key value combination, right? So for every tuple, right, which you cannot change, I hope you know the definition of a tuple. It is a linear storage system where data once fed cannot be changed, right? So it is a heterogeneous one also. So for every combination of row and column, a value, a mapping to the value, right? So even using dictionaries, we can implement sparse matrix, right? So these are the things with which we can work single linked list. So similarly, we can work with circular linked list and double linked list. In my previous videos, I have shown you what a circular linked list is and how the basic operations of it can be done using Python, and double linked list and its operations. So please do follow my channel. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.